Hello everyone, welcome to the fourth experiment for digital logic design students. Today we will learn about digital adders and subtractors. Let's start by the half adder. In half adder, it adds only two single bit numbers and it doesn't take any carry from the previous operation. As you can see in this figure, this is the half adder. There's only two inputs, each input is 1 bit, and there is no carry, but in the full adder there is carry from the previous operation. That's the only difference between these two. We can start connect the half adder circuit shown in this figure and record the data in this table. So let's start in multisim. To do this circuit we only need one XOR gate and one AND gate. So you can right click here, place component, find XOR gate with two inputs and AND gate with two inputs. And we need two different LED to show our outputs. So again, we go here, we search for LED, we take one with color. Also we need ground to connect the other side of your LED. So now let's start by both as zeros. You can also connect this part to this slick and this one to this. That's how it looks. Now we need ground to connect both to 0. So simply can do this one here to connect this part. Now we will see our outputs if both inputs are zeros. You can see that the LED, both of them are not lighting, are not working. So simply can write here 0 0. We can do the second one as well. It says when A is 0 and B is 1. So we need to disconnect this one and we have to find DC power source. And connect the negative side to the ground and the positive to our input. Now run it. You can see that the first LED is lighting but the second one is not, and the first LED is your sum, so you write here 1, and the second LED is your carry out. In this case is not working, so the output is 0 for carry out. You'll do the same for the third case, and for the fourth case you will connect both inputs to your DC power, and then you can find what's the relation between the inputs and the carry output, and also the inputs with the sum output. Now let's move to the full adder. We will need to construct this circuit. So we already have this part, we need to do the rest. We need XOR and we need AND gate and we need another NOR or OR gate.
So just need to select this part.
Search for XOR.
Match it to 1.
Now your circuit is ready. Let's try when all are 0. So this one is to the ground, and we need another ground, because in this case we have 3 inputs. We connect this one to here according to the figure 4.3. Now let's run it and see what's the output. When the inputs are zeros, as you can see here, both LEDs are not lighting, so simply your output for both sum and carry are zeros. Now let's change input A. Note that where's your input A, and change it from the ground to a DC power source. Then run it. You'll see that your first LED, which is the sum, is lighting, so the output is 1, but your carry, the second LED, is not lighting, so your output is yin. So the sum is 1, but the carry is 0. I can also do this case. Your carry is 1, your carry in is 1, B is 0, A is 1. So I need to change the carry input, and we need another DC power. Let's connect it to here, then run it. You'll see that your output sum is 0, but your carry is 1. So here is 0 and your carry out is 1, because if you sum 1 plus 0, the sum is 1, but we have, and the carry is 0, but then 1 plus 1, the sum is 0, but the carry is 1. I can do also the last one. When all your inputs are 1s, now run it. You'll see that both of your LEDs are lighting, so your output is 1 and 1. Now it asks to do this figure as well, but instead we need only XOR and NAND gates, so we delete this one. Now your circuit is ready, so you can run it. Now when all your inputs are 1, so your answer should be 1, 1, 1. Similarly, you can do the rest just by changing your inputs either 0 or 1. After you fill this table, you can answer this question: what's the relation between the figure 4.3 and 4.4? It says what's the difference between these two different figures. And then you have to design and draw a block diagram of 3-bit binary adder using a half adder and two full adders. Only use block diagrams. It says that if you want to add two different numbers, each number is 3-bit binary. If you want to add it using one half adder and two full adders. And that's all for today. Thank you for listening. After you finish, please write your name here and submit it to my email. This is my email. You can submit your Word file, and the deadline is next week, 29th of December.